And we're live. Welcome, everybody. Dr. Armin Mehrabian. He is a data scientist at NASA's Goddard Earth Sciences Data and Information Services Center. What a mouthful. He is focused on supporting open data, open science initiatives, and that is the focus of this presentation today. So, without further ado, the floor is yours, Armin.
Yep, I mean, thank you, Joaquin, for the introduction. And so I'm Armin. I work with NASA GES-DISC, the abbreviation that Joaquin just explain what it is. Goddard Earth Sciences Data and Information Services Center. So before I start talking about what is GES-DISC, my center, and what do we do. Um, I just want to, preface with, what is basically NASA Earth Sciences and our NASA Open Data Earth fleet of satellites. This is just an, overview of some of the satellite missions, Earth science satellite missions that NASA and some of their partners launched over the years. You can see some of these missions started actually in 90s and then through 2000s, 2010s, and all the way to 2024 that is now, and some of the upcoming projects of NASA Earth Data Satellite Fleet. This is just a snapshot of about the data that we offer to the public. As of today, this is actually from a little bit old. Actually, this is from 23. So we distribute a volume of 315 terabytes per day, and we know that, I mean, our numbers for the fiscal year 24 through February has been 382 terabytes a day. And you can see we actually, we're in the process of moving the bulk of our data into the cloud. So we're undergoing that migration. As of now, the total archive volume, including the data in the cloud, is about 102 petabytes. And you can see, some other metrics in terms of, the volume of the data, the number of the files, and these numbers are actually growing so rapidly. Just a little bit about, NASA, what we call the NASA DACS. So what is NASA DACS? A DAC is a distributed active archive center. In the rest of this presentation, I'm going to refer to DACS. So NASA have 12 of these active archive centers across different centers in the country. My team, GES-DISC, Goddard Earth Sciences Data and Information Services Center, is based out of NASA Goddard in Maryland, northeast of Washington, D.C., and we are the largest DAC data center by the total number of the data sets we offer to the public. And so most of my presentation today is going to be about what we do at NASA Goddard to satisfy the goals of our mission, which is to make sure that people can, find our data, use our data, do actual research on data, and each of these DACs, they have, somehow they have their own, area of focus. Our DAC's focus is basically atmospheric sciences, water cycles, and climate change. A little bit more about us. You can scan the QR code that routes you to our website, and we are just one of the 12 NASA science mission directed data centers. And as of now, we host more than 1,500 satellite data sets. We just don't offer, I mean, it's not, we offer data, and also we offer some of the services. We offer services such as subsetting. And for those of you who are not, you don't know, what is subsetting. Earth data is complex. It, depending on the mission, it comes in, data files we call like granule swaths and different things. So you want to be able to actually retrieve the data for the time and location that you want. So we offer many of these services, and I guess one of my team's most known services is Giovanni, which is a visualization tool for some of our data at GES-DISC, and even some of the data from the other DACs. And you can see some examples of the visualizations we provide here. For example, the bottom right, you can see this time series area average of heat flux monthly. This was essentially just created. I just created like a few minutes before this presentation, and we're going through this heat wave, and you can kind of see this heat flux, which is by proxy can be translated into a measure of temperature. Just you can see the spike all the way to the right, and on the top you can see a time series map of the liquid soil moisture. You can actually we can produce for you these animations. I guess the time for this one is from 2010s all the way to the most recent measurement, which was a few days ago. So we offer data, we offer services. Now, as a data provider, we always ask ourselves where the knowledge exists, and not just the data, but actual knowledge, because we want to make sure that users can not only can find our data, which is not trivial in itself, but also they can get the data, download the data, do actual research with the data. Earth data is complex. If you haven't ever downloaded one of these data sets, you will see that they come in formats that may not be common, things like HDF5, NetCDFs, and when we open them, there are a bunch of variables in them, actual physical measurements. In some of the data sets that we have, they can have hundreds of, I guess, measurements. So the bottom line is that it's really hard for an average scientist to find the data that they need, and we want to make sure that the users find that. So the question is where the knowledge exists. So if you go on our website and you look up something, a keyword like precipitation, imagine that you have an application or research that wants to actually use some precipitation measurements. Traditionally, the way that search engines work is you have a data curation team that every now and then that a new data set comes in, the data curation team go and create these metadata for that data set. And on the left hand side, you can see some of the fields that exist in a sample data set. Things like the spatial coverage, the distributed organizations, some of the related keywords that are science keywords that these data sets are tagged with, temporal resolution, and so on and so forth. So this is the main way that traditionally these search engines work, and we also for the most part rely on this method. The second source of knowledge is actually data documentation. So if you go on a particular data set landing page on our website, at the bottom of the page, you see we have all these documents, PDFs listed. And these are basically the readmes, the algorithms, and all the details that how this data set was generated from raw satellite measurements. And these PDF files can have like hundreds of pages themselves. And these are not naturally the information, the knowledge within these files are not captured, are not discoverable by the search engine. So this is a huge important source of knowledge that we need to be able to to tap into for better search and discovery. We also have things like how-tos and FAQs. We have a team that commonly on a regular basis they go and create these amazing how-tos, how to download data, how to do different things in different environments. For example, how to pull data into Jupyter Notebook, do measurements, a lot of things. How to connect to the cloud, and so on and so forth. So this is also these are some other resources that one can use to kind of narrow down the scope of the data that they're searching for, and hopefully they land on the data that they need. So the focus of my presentation today is going to be publications. What are publications? So publications are basically people use our data, and ideally they publish some research using our data. And one of the things that we do at my team is basically we track all these publications that use our data. And if you really think about it, the people that search our data sets, they download the data sets, they do actual research on a data set, and they really, they do due diligence, do research, publish something. They're the most devout users of our data, and there's a lot of knowledge that is basically buried within these publications, and we want to be able to look into all this resources of knowledge, and kind of use this community that is using our data in our data discovery process. For example, what I'm showing to you on the right is the publication search part of our website, and you can see for a particular keyword like precipitation, here you can see a list of publications that have used our data, and some of the data sets that they have used in that publication. And a lot goes into how we collect all these citations, and how we know what was used in those publications. And in the barcode, in the bar chart on the left, you can see the growth of the citation of our data sets within publications. Yeah. So at the high level, we create this knowledge graph that is meant to serve as an infrastructure to help us build knowledge retrieval applications, and help us in this search and discovery. This is a high level schema of our knowledge graph. This is a simplified version. There's some nodes and edge types that I'm not showing here, but at the heart of this knowledge graph, there's a data set, and this data set can be cited in a publication. A data set can have many variables. A data set has science keywords. These are the keywords that it's tagged with. A data set has a platform, which is the satellite mission that it was actually derived from. The mission itself, or the platform, has instruments, actual physical instruments that carried out the measurements, and how-tos and FAQs. And there are some documentations for the data set, as we discussed. Now, this slide is a little bit 1 or 2 years old, but this shows the power of knowledge graphs. Because a few years ago, if you went on our website and type something like landslide, you would just find no data. You would just find one or even no data set, because of all the data sets we have, just one of them had the keyword landslide in the name, or it was tagged in the data metadata with the keyword landslide. But we know that there's many other data sets that people have used from our data catalog to do landslide research. So one of the ways that this connection between the publications and data sets through this knowledge graph helps us is that we constructed the linkage between the publications and data sets, and also we went one step further, and also found the publications that cite those publications. And you can immediately see this graph was back then built in Neo4j, and you can see with a simple graph query, we can now just not only scan the dataset metadata, but also the text of the publication. And if landslide was used in that publication, then we know that which dataset was used in that publication. Maybe the dataset is a good candidate for landslide research, and offer that dataset to the user. The query can be a little bit more, complex, something like Agile-Bloom. This is another example. This did not show up. This term did not show up in any of our data sets, and none of the publications that we collected that cite our data set. However, we have the publications that cite those publications. So if we we go one step further to two-hop connections, we can see that this term Agile-Bloom was cited in a publication, that that publication cited another publication which cites one of our data sets. So maybe you can say by proxy this publication used some of this data. The other advantage of this knowledge graph is that once you restructure your data in this knowledge graph format, you can apply a lot of graph analytics. For example, here you can use centrality measures like PageRank to rank the publications in this citation network of publications and data sets. Because at the end of the day, when you're doing a search, it's a two-step process. In the first step, essentially, you identify the candidates, and then there's a second step that does the ranking for you. So if we want to find publications, here, for example, I'm showing, I guess, this is for precipitation. If we search publication for the term precipitation, a lot of publications and data sets actually show up. And the question is that just based on that one keyword, which publication should come to the top? And we can construct this PageRank centrality algorithm that tells us which of these publications have more influence in this network. And those are the ones that, if PageRank, it does not only depend on the incoming publication that cite that publication, but also the validity and reliability of those publications as well. So this is a great way to actually sort this data and provide some insight to the user which publication to look into, and as a result which data set to download. And yes, this is just showing the simple Cypher query to do this PageRank algorithm. Another thing that we can do is dataset recommendation. One of the beauties of graph is graph embeddings. So once you create an embedding out of your graph, now when a user comes in and it's they go to a dataset landing page, we can actually offer similar data sets based on the topology of this graph. And here I'm showing, for example, for this OM SO2 data set, now we can give some suggestion, recommendation based on the topology of a graph, as opposed to some language methods that is just purely based on the linguistics. And one of the advantages of using a graph is that it's a little bit more explainable. So if I'm suggesting this ML2 SO2 suggestion for OM SO2 data set, I can look into the shortest paths, or all the paths that connect these data sets, and kind of get an insight why this data set was recommended in the first place. For example, in this case, we see that these two share many science keywords. Even a publication cited both of these data sets, and they're coming from the same mission, the satellite mission that is called Aura. So it's a little bit more explainability in terms of the recommendation. You can do other things with the graphs. One of the ways that we actually use graph through graph machine learning is to do missing link prediction. So each data set is being tagged with different things. For example, the science keywords that our data curation team actually finds appropriate for that data set. But you would see that there's some keywords that would apply to that data set, but may be missing. Or some of our oldest data sets, they don't have these linkage properly. And through the link prediction algorithms, actually machine learning, we can predict some of these keywords with really good probability actually. And the QR code that I'm showing here, we recently published a subset of our graphs on Zenodo and to be to the public, and we framed that as a machine learning link prediction task. So if you're interested in graph link prediction, I guess I would highly recommend you to go and download that data set and run your algorithm and try to predict what links are missing in our dataset metadata. And we are in the process of publishing the full graph. When I say full graph, I mean not just for my team, for all the NASA Earth observation satellites across different centers in a month or two. The other thing that actually we do with language models and the graph is that as I mentioned, we have this documentation that have a lot of information, these PDFs about what are the details of the variables that are in a data set, and they come in like large PDF format, tons of tables, and through some with the recent advancements of language models, now we can actually create a prompt that says go and directly look for the measurements in this PDF file and construct the sci-fi query that would input those basically ingest those inferred knowledge into the graph itself. So actually this goes back and looks into the tables in those files and then tries to extract the knowledge and put it back to the knowledge graph. The other thing that we can do with this marriage of the language models and the knowledge graph is that as opposed to traditional search that was primarily based on curated metadata, now we can actually use them in a graph rack. I guess many of you may be now familiar with RAGs, retrieval augmented generation, and graph rag is basically the same concept but based off of a graph as the knowledge base. So what I'm showing here is that we can now, using the knowledge graph that we have ingested our dataset metadata, all these documentations, how-tos, FAQs, publications, so on and so forth. And now, instead of just doing a keyword search, we can go and ask, really complex questions. I was in one of our Earth Science, data-focused conferences a year ago, and I asked this question from the audience, and there was just one gentleman that half confidently knew what was the answer. Maybe the other ones were shy, but if you ask something like, in what way OMI and TROPOMI data products are different? I'm not a scientist, but I can tell these are two data sets, two essentially class of data sets that offer similar products. And the question is, how are they different? And for you to answer this question, you have to sift through huge amount of data in all those PDFs or publications. So like every other RAG, the way it works is that you have a language model that works as your embedding, and in the first step, you find some candidates within your graph that may contain it contains the answer to your question, and in the next step, you pass the question and also the candidates to a second generator language model, and it constructs for you a generated response. This is again an example of that question. There's no way that you could ask this type of questions using a text-based search in traditional search. But here, once you actually ask this question, and this is the response, and the response gives you really very detailed differentiations between the two types of OMI and TROPOMI data products in terms of spatial resolution, coverage, instrument configuration, and format, and so on and so forth. This is really exciting, because as a researcher that comes to our website, you would wonder, okay, which data product I should use. For example, if I want to do some research on ozone, if you search for ozone, you'll see we have a lot of data sets that have ozone measurements, and each of them have different types of measurements. So this really comes handy and useful for scientists and researchers. I talked about the RAGs. So I just want you to focus your attention on two foundation models that NASA and IBM trained recently, and they shared these models in public. This is an effort carried out by IBM and NASA impact team, and the left one in this is a language models is actually a suite of language models for scientific application. This was recently actually posted on the Hugging Face under the NASA impact repository. And we used a corpus of earth science, biology, physics, geophysics, planetary sciences, and astrophysics to pre-train this model. This is just an encoder model. It means that it does not do generation, but you can actually take it, use it as embedding, or maybe fine tune it for some downstream application of the science. And we are publishing some results that show that how this outperforms a same size model, but not trained on this corpus of scientific text. And the right model the model on the right is Prithvi, is a foundation model for geospatial data. So it's actually a vision transformer, and it was trained on a data set of a 1 terabyte data set of HLS, which is Landsat Sentinel-2 data set. And this can be really also helpful if you want to do some computer vision type of application on geospatial data, things like wildfire scar detection or segmentation and crop segmentation, irrigation, and that sort of thing. Both these models are publicly available, and I highly encourage that everybody goes and downloads these data, these models. We also have the data, the benchmarks that we use to evaluate these models, and the data sets that are used for downstream tags with tasks with these models on the Hugging Face. And lastly, this is my last slide, and this is kind of a prediction. And the last source of knowledge for us is the actual satellite data, the pixels. So a lot of the search and discovery these days, traditionally have been based on text, all the metadata, all these publications more recently, and you can imagine these are like more the description of the data. But with all the advancements that we're seeing now with multi-modal modal models these days, I think in near future we should be able to actually link the actual pixel measurements, the content of these images, to knowledge, and really have a more kind of comprehensive view of what this data represents, and and help the scientists to use and do research on this data. With that, I want to end my presentation. I thank you all for listening to this presentation, and if you have any questions or comments, feel free to reach out to me on my email or on my LinkedIn.
Thank you very much, Armin. I want to just underscore the importance of this work in terms of researchers and new machine learning engineers, or anybody working with these machine learning models. I don't know if it was, something that I know for a fact, like I've heard expressed as a serious pain point with people that want to get involved in the open data set, open model, open everything space. But even if you go to like a Hugging Face or a reservoir of information, it's opaque because sometimes the model may be available for you to use, but you might not have access to the data set or the methodology that they use to train the models. Or it might be under some NDA, or it might just be restricted because they didn't hold that in the right way or store it in the right format. Um,
Absolutely. I mean, so NASA has this. I mean, I know this. You're familiar with this. This Transform to Open Science program. It's a mission called TOPS. So you got to look it up. They actually have courses for for that free courses that educate public about open source and open science. And if you actually go on those Hugging Face links, first of all, they both those models, they have a publication attached to it. And also, I mean, there's the benchmarks. We also publish the benchmarks and codes that we use for that. The data that was used, I mean, for the language model, because of some contractual obligation with the publishers, I mean, that was not, we couldn't, we couldn't, obviously, we're not at the liberty of publishing that. But with the foundation model, the vision model, the data is actually that the model was pre-trained on this HLS dataset, which is again a part of the NASA open dataset. So the dataset is there, the model is there, the publication about it is there, the benchmark is there. Please go and use it, and make sure you cite it properly, because as someone that is tracking these citations, usually people, they don't cite these datasets properly, which they should do it by DOIs. But yeah, make sure to cite your resources properly, so that we can actually track your research on our side.
yeah, thank you very much. I think it's a boon. Um, yeah, so I look forward to seeing where this goes next year. I know this has just been released, and there's additional initiatives that coming out of NASA to reinforce this. Summer programs and additional TOPS courses coming up. I think
Yes.
the 101 series just dropped, and it's all free, so there's no reason why anybody shouldn't take advantage if they want to get involved in a more scientific, open science space.
Absolutely, yeah.
All right. Well, we're going to take a short break, and we're going to have the next presentation. We'll see you in approximately 5 to 10 minutes.
Thank you.